Okay, welcome to class. We will start with our beloved reading quiz. And the first question of the quiz is the following. The bond angle along the single bonded carbon backbone of a polymer is 66 degrees, 90 degrees, 109 degrees, or 120 degrees. Okay, we're going to wrap this poll up.
I need to decide what I'm sorry.
Answers in. Phone a friend if you need. Okay, we're ending. Okay, good. 94% of people got that right. The reason why is because carbon has 4 bonds, so it forms tetrahedra, and the angle between two sides of a tetrahedra is 109.5 degrees. Okay, the next question. The number average molecular weight is typically a larger value than the weight average molecular weight. True or false? Okay, we're going to wrap the poll up. Get your answers in. True or false? The number average molecular weight is typically larger than the weight average. The answer is false. We're going to get to that later today. Okay, last reading quiz question. Thermoset polymers, like epoxies, are cross-linked network polymers and therefore tend to be higher in crystallinity. True or false? Okay, we're going to wrap the poll up. Okay. True or false? Again, it's false. So I will go back and probably correct that too, because people are missing it. Okay, so two announcements. First is that the midterm review will be in this room tonight. We're doing that tonight from 5 to 7. I guess 3 announcements. A second announcement is that the practice midterm has been posted and the solutions will go up tomorrow. I'll post solutions to the homework which you just turned in by today. Yeah, I think that's it. Okay, learning objectives for today. Yeah?
Is there going to be a review tomorrow night as well, or is that not going to be?
It's up to the TAs. Their review tomorrow night or no? Christian's getting married, so he's busy. But Emily, maybe watch for an announcement. If she decides, if you can sway her to do it, then she'll hold the session. Yeah, other questions?
Will you be recording and posting the review?
Yeah, I always do that. I will record it and post it as soon as I get home, so you should be able to see that available. Other questions?
Is this test primarily chapter 9 and 3?
Good question. So, oh yeah, that's the other announcement. You can take 2 sheets of notes, right? So you can bring your own from your last test if you want, because this test will be comprehensive. The reason I do that is because our civils are bugging out after this. This is their final exam. So there, and you know that if you saw the study guide, I put that there's free energy on here. So that was from the last test. It's coming back on this test. You can have 2 sheets of notes though. The other 2 questions, so 1 question is free energy, the other 2 are on fraction mechanics, crystal structure stuff. Okay, other question? Chapter 3. So this stuff that we're covering today, all the polymer stuff, that is not on this exam. That will be on the 3rd midterm. Okay, any other questions before I move on? Okay, we're going to keep going then. Today's learning objectives, we're going to introduce you, I at least want you to be familiar with some of the important types of polymers. The stuff that you've probably heard of before and wondered what it was, like PTFE or polystyrene or polypropylene. We'll introduce what those things are today. We'll talk about molecular weight and degree of polymerization. We will differentiate between thermoplastics and thermosets, and then we'll talk about how different structures are possible in polymers in terms of side groups, if they're the same side or different side, or if they repeat. We'll get to that. And if we have time at the end, we'll get to crystallinity, but that might be on after the break. Okay, we already talked about polymerization. Again, this is a recap of the polymerization process. I've written it in words here, but I think it's easier to see schematically. Again, you start with a monomer, and the monomer almost always, doesn't have to, but it almost always has a double bond, and you're going to attack that double bond, thereby creating a free radical on half of your monomer. That monomer that's now been radicalized will attack another monomer, and then continue polymerizing, right? So let's start with our very first polymer. Yeah, Rosa?
How does that process stop? I mean, if it's a
Great question.
only have a certain amount.
Great question. Let's say you've got a pot of this stuff. You're doing it on your stove at home, right? You've got a bunch of monomers cooking up in that pot, and you drop in 1 single bromine atom, then feasibly, you can imagine a thought experiment where that just chain reacts all the way until it polymerizes every single monomer, and your pot is now 1 gigantic chain of polymers, right? So that's a fine thought. In reality, that doesn't usually happen because we don't add like one initiator at a time. The initiator is the bromine. It initiates the polymerization. We add some number of them. So let me ask you this. Maybe at this, turn to a neighbor. If I triple or double, the amount of initiator, what should that do to my chain length? Chain length, how long is the polymer?
This is what we're going through today.
Okay, what do we think? If you increase the amount of initiator, what do you do to your chain length, and what's your rationale? Let me pick on somebody who's never said something in class before. Anybody? Ari, have we ever called on you?
Yep.
No. Ari's out. Josh, we have. Elsa, we have. Next to Elsa, I don't know your name.
Amelia.
Amelia.
Yeah.
What might happen?
Like the length would get shorter.
Length should get shorter, right? Right? You start it in a bunch of different spots. They're all going to keep on reacting, and then when you're out of monomer, the reactions stop. So you should have a shorter chain length, right? So you can change things like that during the polymerization processing to tweak the type of polymer you get out of it. Because molecular weight turns out to be a pretty big indicator of some of the properties we care about. By the end of class, we'll know why that is. So this is not a class that's going to spend much time talking about processing of polymers. We have a course in our department that's just on polymers. If you want to learn more about it or other ways that you can create these things, I suggest you take a look at that. Okay, let's talk about polyethylene. Polyethylene is by far I think it's the most common plastic. I'm pretty sure that it is the most common plastic and the most frequently used. They use it for everything from packaging to parts to bottles, all over the place. And if you look at your component, whatever it is made of plastic, I don't know where this came from. If it has a little recycle symbol and it says LDPE, HDPE, MDPE, those are all different flavors of polyethylene. Low density, high density, or I assume that's medium density. There's actually other ones than this, right? So, and what that's referring to is the chain length, right? How long is this chain is really what that's referring to. Okay, so what does the structure of polyethylene look like? It's a carbon backbone, and off of every single carbon, you've got hydrogens. Right? So we could draw these things. These are all hydrogens. So it's kind of a boring polymer. because it's just ethylene, which is a boring monomer that you polymerized into a boring polymer. The ends technically need to have this. They're going to have, carbon's always going to have its 4 bonds, right? So you have to put 3 hydrogens on the ends. So when we talk about this, we usually talk about the repeating unit, and the repeating unit, they usually draw like that. That's the repeat unit, right? So the repeat unit has a molecular weight. It's got 2 carbons and 4 hydrogens, right? So it's going to be 24 plus 4 more, around 28, right? The repeat unit has a molecular weight of around 28 grams per mole, okay, in this structure. Let's go to our next one. Polytetrafluoroethylene, or teflon. Yeah, question?
When you're polymerizing it, what happens to the bromine after the reaction?
One more time. Why doesn't
What
what?
happens to the bromine or the chemical that initiates?
So if you started with a bromine, then it is hanging out on the end. You'd have bromines. Yeah. If that's what you use for your initiator. Okay? And you don't only have to use bromine. There's lots of other initiators out there. Sometimes just heat. You heat these monomers up, and that thermal temperature is enough to break the bond, and then they start polymerizing. But yeah, you're exactly right. Okay, Teflon is something you guys have heard of before. It's non-sticky, right? In fact, it is the only known material. This is pretty neat. Will this video work, or will it take me to somewhere horrible? Which happened before. Okay, here you go. Here's our gecko trying to climb up a Teflon pan. Not happening. Not today, gecko. Right? So, your van der Waals forces from the feet of the gecko, it cannot even stick to that. And they can stick to everything, right? Teflon is the only thing that they won't stick to. So what makes this thing such a not sticky material? What makes it such a non-sticky material is the fact that you've got carbon bonded to fluorine. Now, in terms of bond strength, is that a strong bond or a weak bond? That's a strong bond. Fluorine really wants those electrons, right? And so once it creates that, if you introduce something else that's less electronegative, it doesn't want that electron as badly as fluorine does. So you put this thing in nitric acid, it doesn't care. That, you know, that oxidizing agent, it doesn't break that bond, right? So because this thing is extremely chemically inert, it won't react with a lot of things. In fact, I don't know what it does react with offhand. Probably something. I can't think of it, right? Low friction, because things don't stick to it. So if you were going to make skis and you wanted to have really low friction while you're skiing down the mountain, and you're going to put wax on your skis, there's paraffin wax or there's fluorocarbon wax, and that stuff is better, has a higher wetting angle, and it's less friction, right? So it's good for a lot of things. They'll use it for all sorts of other stuff, right? Let's skip that. Again, so the repeating unit is right here. It's C2, but now 4 fluorines, right? And then N just tells you that's how many repeating units there are in your chain, right? So if N was equal to 100, we call N our degree of polymerization. Degree of polymerization. And you can figure out the chain length from the degree of polymerization and knowing what the monomer is, right? The monomer, this repeating unit, you know that it's equal to 2 carbon bonds, and there's 100 of those 2 carbon bonds. So you know the total chain length is 200 of those. That becomes important when we try and calculate chain length. Okay. Next up, let's talk about polyvinyl chloride, or PVC. So in this one, you start out with polyethylene, but you swap out one of the hydrogens with a chlorine molecule, right? Or chlorine atom, I should say, right? By putting that chlorine there, you've created polyvinyl chloride. And they use this for all sorts of stuff. Pipes and stuff, or this thing is everywhere now. You can buy pantaloons out of it, as you can see here. It has some pretty good properties. It can be made rigid or flexible by adding other polymers to it. And just in and of itself, it's actually a pretty rigid polymer. But if you add things to it, you can make it more flexible. So if you wanted to make pantaloons out of it, you could. You've got polypropylene. Polypropylene, it has a repeat unit that looks like polyethylene. Again, these are all, when it doesn't show it, they assume that you realize that those must be hydrogens. So if they draw nothing, realize that those are hydrogens, because carbon has to have 4 bonds. But they've taken one of the hydrogens away, and they've replaced it with a methyl group, which is CH3. So methyl, that's a pretty big group, right? Chlorine is a pretty big group. Methyl's probably a little bit bigger. And by putting that, you are adding something along the side, which we say adds steric hindrance. Steric hindrance means that when something's sticking on the side, it's so big that it limits how you can put another molecule next to it, right? So if you had if you're trying to park like cranes in a parking lot, and the crane thing is sticking off to the side, and you can't pack them as many in the parking lot, right? They'd be bonking into each other. That's basically kind of what these things do. And if they can't get close together, we learned from last time that that reduces the forces between those molecules and therefore makes it lower melting point. It changes its properties that we care about, changes things like mechanical properties too. Okay, next group, even bigger steric hindrance is if you put a benzene ring on the side, right? So this looks like polyethylene, but now every other carbon has one hydrogen replaced by a benzene ring, which is a carbon 6, hydrogen 6 ring sticking off the side. I guess it's a benzyl ring because it doesn't have 6 hydrogens. It's got 1, 2, 3, 4, 5 hydrogens, and the 6th spot is where it's attached to the chain. So it's a benzyl ring. Okay, this makes if you make it fully dense, it can be pretty rigid and hard and brittle. But that's not how we normally use polystyrene. Polystyrene, we normally don't make it fully dense. We actually make it such that it has lots of air inside of it, and this is your styrofoam, right? Styrofoam cups is polystyrene. And the reason we do that is because all the air pockets inside of it reduce the thermal conductivity through it, so you can make things that won't burn your hand. You can have boiling liquid in there, no problem. Okay. And actually, again, let's hope this video goes where we want it to. You can actually boil an egg in a styrofoam cup by just putting it in the fire with water in it. Okay. Inside there, you could drop an egg in there or whatever else, and the cup is not burning, the water's boiling. So what does this tell you about the structure of polystyrene? Any thoughts? Turn to a neighbor. What do you think this inherently tells us? The fact that cup is not burning, what must be happening? And again, you can melt polystyrene. You can take it from that cup, and if you heat it up, you can melt it. It will turn into idly piddly on the ground and eventually catch fire. That's not what's happening here. So any thoughts? What might be going on? Ryan, did I see a hand?
Oh, I was just going to ask, is the steric, is it the same as like steric?
Steric, yeah, same thing. Same difference. Okay, any thoughts? What might be going on? Why is that thing not melting or burning? Yeah.
Well, someone else was mentioning that, I mean, you can do this with the chamber cups as well. Basically because all the heat is transferring from the outside cup to the water. The water has such a high specific heat capacity that it just boils and basically takes all the heat away from the cup.
Yeah, so the water will increase in temperature, right, and in doing so, it will absorb energy. Once it hits 100 C, it stops increasing in temperature. So what's it doing after that? You have your enthalpy of fusion, or vaporization, excuse me, where it's boiling, right? And what's really happening here, even in a paper cup, or like a cup, like take like a red Solo cup, like something like that. If you put that in the fire with water in it, it's probably going to melt. So what's happening is this is a porous cup. Water molecules can come through, and they can vaporize at the surface, right? So it doesn't come through a lot, but enough can come through that it vaporizes, and in doing so, reduces the temperature of your polystyrene so it doesn't melt.
So how does that work with the paper cup, though? Is it the same porosity?
You must have some porosity. Water vapor, probably not water liquid, but water vapor can have some permeability through it. Okay? And again, we use these as foams in packing materials, and this is becoming a big problem because in the year 2017, we just Amazon everything to us, and it comes with packing. And if you've noticed, this is why there's not as much styrofoam in those things, because you can't recycle that very easily. It's not economical, it's not easy to do. And so now they're doing these big air pockets, right? And that's polyethylene, I'm guessing. I don't know offhand. But those are recyclable, right? So that there's been a change over the years, and I think you'll see that trend continue. Rosa?
What makes polystyrene and its like different parts not recyclable?
Great question. We will have a whole chapter on sustainability later this semester, so I'm going to pause that thought for now. I'm glad you're asking it, but I'm going to answer it later when we talk about why are some things recyclable and one thing's not as. Yeah, is it Barzan? Yeah.
I've seen a video of people dissolving those like polystyrene cups in is it benzene, I think?
When they make the flammable gel, or what?
They were just dissolving it directly into, I can't remember what it was, I think it was benzene.
Okay.
So can you use that to recycle it or something?
I don't know if you dissolve in benzene, but it wouldn't surprise me because you have a big side group that's a benzene, and we know from Gen Chem, if you learned nothing else, hopefully you remember that like dissolves like. So if you're trying to dissolve something that's polar, you want to use a polar solvent. If you want to dissolve something that's apolar, Basically, so it wouldn't surprise me if that was soluble a little bit, and that might be a method to recycle it. So again, to give you a brief answer on recycling, a lot of things that are technically recyclable just aren't, it's not something we can do at scale at a reasonable cost, or without other negative impacts that we haven't considered yet. There's PMMA. This one's getting harder. Polymethyl methacrylate. Sometimes they call this acrylic glass. If you go to the craft store and you buy acrylic glass, it's not glass, it's a polymer. And what it is, you've got the carbon backbone like usual. You've got one carbon that's got the 2 hydrogens. The other carbon has a methyl group, which would make it look like polypropylene if this big thing was a hydrogen, but it's not. This has a carbon double bonded to an oxygen, carbon single bonded to an oxygen, bonded to a methyl group. So polymethyl methacrylate, I don't care if you don't remember where the names come from, you learned that stuff in OChem. What I do want you to know is that this is used as a lightweight, shatter-resistant alternative to glass. And another really good alternative, if you want an alternative to glass, like silica glass, you can use polycarbonate. Polycarbonate is what they use for bulletproof windows oftentimes. It is extremely very good for that. What's interesting is it's very tough. It absorbs a lot of energy and therefore it won't shatter when you shoot it with a gun, but it will scratch easily, right? So CDs used to be made of polycarbonate. I think they still might be if anyone's using CDs still in 2017. But your CD would get scratched really easily, and then that just is the worst thing that ever happened. So then they would put down a hard layer on top of it to keep it from scratching.
So,
yeah.
my question is, why don't they use polycarbonate more for like regular bulletproof vests? Do they do that?
There's better materials for bulletproof vests. They use polycarbonate for bulletproof things when you need it to be transparent, because polycarbonate is transparent, so you can make windows and stuff out of it. But there's better things like Kevlar, which is and other materials that make better bulletproof vests than polycarbonate. We've got bakelite. Oh yeah, question?
So for homework and tests and things, should we be knowing all of the names and all of the uses of all of these things, or are they more just background information?
The uses is background. That's just, you're engineers and I want you to know this stuff. But on test, I'll make it clear which one of these things you need to be able to say draw the repeat unit of, and it won't be polymethyl methacrylate. It'll be ones like polypropylene, right? Carbon-carbon, 3 hydrogens, and a methyl group. That's easier to do. So I'll make it clear which ones you need to know. Just like on this coming exam, we talked about a lot of crystal structures, but you only need to be able to know maybe 5 or 6 of them. It'll be something similar with polymers. You'll need to know 5 or 6 of them. And most of them look like polyethylene with 1 or 2 substitutions. Okay, you got bakelite. This was one of the very first synthetic, you remember from last class, one of the very first synthetic polymers. This was used all over the place. They made phones and jewelry and all sorts of stuff out of it. Kitschy stuff from the 50s is probably made out of bakelite, right? What's interesting about it is this is the first one that significantly deviates from polyethylene, and does so in 2 ways. First off, it doesn't have the polyethylene backbone, and then the second point is it doesn't have a backbone at all. This is a 3-dimensional, or what we call a network polymer. Instead of being a long chain, which has been everything else we've talked about up till now, this thing is 3-dimensional, because you've got these units which can connect in more than 2 sides. If that only connected front and back, you'd end up with a chain, but they can connect in 3 sides, so you get 3-dimensional structures out of them. Network polymers tend to be more rigid. Remember from the clicker question today, they tend to become more rigid. They tend to have higher temperatures of melting and that, but they don't necessarily have to be more crystalline, because this is a jumble. This is a jumble of big funky molecules. Chains can line up next to each other. You can end up with rows of chains, so they tend to be more crystalline than something like this. Okay, next polymer I want you to know is nylon 6,6. Nylon stuff like the Bowflex is made out of. If anyone out there is still using their Bowflex, nylon 6,6 is there. The reason they call it nylon 6,6 is because you've got 2 sections of your chain that have 6 carbons each. Let's see, that's carbon, 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 carbon. So that's 6 right there. Nitrogen, that's an amide group. Adipamides, so amides are your nitrogens bonded to hydrogens. Then you've got carbon, 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 carbon. So you've got 2 6 lengths of carbons, right, that look like polyethylene. And then you've got stuff in between them. You've got these, these oxygens double bonded off the side. So again, probably not something I'd have you draw on a test, but yes, this is an important polymer. That's a pretty big repeat unit too, right? So the degree of polymerization, if you've got 2 chains that are equal distant, and one is polyethylene and one is nylon, the degree of polymerization would be higher for which? Turn to a neighbor. Degree of polymerization being N. So yeah, one more time. If you have 2 polymers that are the same physical length, let's say you could stretch them out, and they're the same length. One is polyethylene, one's nylon 6/6. Which has the higher degree of polymerization? Okay, this should be straightforward. Cody? Polyethylene definitely should be more, because for every 1 mer unit of nylon, you've got like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bonds along that distance, right? Polyethylene, you've only got 2. So it should be, 7 times less, right? That's assuming that all bonds are the same length and that we can stretch it out all the way, but it's a pretty good approximation. Okay? Yeah.
Are there different types of nylon where the spacing between?
Yeah. That's why nylon 6/6 is its own, and there's other varieties. Yeah. And actually, this makes for a sweet demo. Let's watch this. This is pretty cool. You can make nylon 6/6. Oh, this one's 610. Same thing. Not the same thing. Similar polymerization process. Not the same thing. Right? When you make this, and this is a good time because I need to talk about our random assortment of objects up here, which I forgot about somehow. So I need a volunteer. Can I have a volunteer? Come on down, Jeff. So we have a can here of Dole mandarin oranges. Put your hands over this. Right there. That's the spot. Dead. You're going to your hands. Those are all yours. You can have those. Take that with you. And most of the food is just empty. Here we have a can, and it was filled. That's good. You've got a can that was filled with an acid, and yet this is not corroded inside, right? We just learned, we spent like weeks learning about corrosion, right? Weeks learning about how easily metals are corroded, and here we see no corrosion inside of here. So what's interesting is that in the inside of every single food and beverage can like this, there's actually polymer lining. There's a polymer lining there that just, if you remember Randy, the corrosion guy who came and spoke, kind of rambled for an hour. He spoke about painting things because it prevents corrosion, because it prevents the salt from getting there. That polymer is doing the exact same thing. It's providing a salt barrier, or an acid barrier in this case, that prevents it. So you can actually find anything. If you dissolve away the metal, let's say from the outside, you would see a polymer bag on the inside, and that's happening right now as we speak. But it's not done yet. So we will post a video, or maybe I'll bring it to class after the break. It's still dissolving. I think the problem with our can of Mountain Dew that we're dissolving is we didn't sandpaper the paint off on the outside. They have a little bit of paint on the outside. So it will be ready soon. Yeah?
Are there issues recycling those or things in general with those linings?
Great question. Yeah, if you're going to recycle this can, which is probably steel, I don't know what it is, probably steel, what do they do with it when they recycle? Again, in a few chapters we'll talk more about it. We're probably going to melt this, and that polymer is going to burn off. And it's not all going to turn into CO2 and float away into the atmosphere and cause global warming. Some of it is going to stay put in your vat of molten steel and change the carbon content of your steel. So yeah, it does influence it, but it's not a game changer because it is a very, very thin film. Yeah, Anthony.
So I hope this isn't outside the scope of what you want to get at. How do you use that polymer with this reactive with some sort of solvent?
To get rid of it if you wanted to?
Yeah, like say, for example, you want to control someone on the internet and forward out of tin cans or steel cans or whatever.
Okay.
You want to get all the impurities out of it. You just soak it in acetone or something like that.
To get rid of the polymer?
Yeah.
Yeah, first of all, I don't know what polymer it is, but you would pick something that dissolves that polymer.
So you'd have to research.
I don't know if it's acetone, it would depend on what it is. Okay, our next awesome demo for today comes courtesy of Logan, who brought us hot dogs because I forgot to get hot dogs. So we're talking about something called a copolymer, and nylon's our first copolymer that we've come across. So you have, with a copolymers, you have different repeat units. You have one delicious classic uncured wiener unit, and you have one delicious crunchy Cheeto unit, right? And you can put these together in any way you want. You can choose, if you so choose, you could put them alternating, like so. You could do random. You could do a couple in a row. You can do whatever you want. right? And this is why polymers do amazing things. I think we're done with these, unless anybody wants to eat these. These are now freaking, we'll just pass these around. I'm not taking those home, so you guys need to eat them. Okay, that is the big, it's as simple as that. That's copolymers, right? They can be different names. It can be random, or they can be block. They can be alternating. We're going to introduce the names in a minute, but all it is you started with different monomers in the pot, and you polymerized it in such a way that these things make a chain, right? And we can watch that now with nylon. Nylon's pretty cool. They're going to add the two different. They're going to add the Cheeto and the hot dog in a beaker, right? So great, right? And if you see what happens, they're gonna add it. Then they're gonna reach in with a stick, and they're gonna grab the end of that, and they're gonna start to draw out. So these things, they're different densities, so they're gonna float at different levels, and there will be an interface where they're touching, and that's where the reaction is gonna start. So he's gonna reach in and grab it at that interface and start to pull it out, and it does something pretty rad. So this is not how they do it industrially. This is like a demo, but this is how you can make nylon fibers, right? It's gonna reach in with some tweezers or something. Some chemistry real quick. There's your two groups, your Cheeto and your hot dog. We would do this, but it smells pretty bad. I did this once, and it smells not great. They're going to grab the interface, and now as they draw this out, it's going to keep on creating a new interface where those two will start to react with one another. And if you wrap this around a rod, you can actually make fibers, right? So this makes a big chunky fiber, right? If you wanted to make thin fibers that go in whatever the object is that you're making, you would control this process a little bit better. But this is the basics of it. You're going to mix your two polymers. In this case, they react automatically, and they create, they give that off actually. So that solution that's left over is hydrochloric acid rich, right? Because it's creating that. So this is what we call a condensation reaction. Again, we're not going to cover that in this class. If you take your OChem, you learn about condensation where it's water coming off, or whether it's something else. In this case, it's condensation of a hydrochloric acid that's coming off, and those two things react with one another. Rosa?
So, is a different version of that how to make like pantyhose?
I don't know what pantyhose are made of, but I'm going to Google it later today. So I don't know. I can't answer that question just yet, but now I'm curious. Other questions, Zach?
I once saw a demo where they took like carbon nanotubes and they used the Tesla coil to arrange them. Can you do that with the polymers?
Good question. We will get to magnetic fields later on, and we'll talk about what type of materials interact with magnetic fields that would be created by the Tesla coil. So hold that thought. We'll come to it in a couple weeks. Okay, next polymer I want to talk about is PET, polyethylene terephthalate. This is the stuff, and they've got like lots of consonants in a row there. Terephthalate, right? This is what they used to make like Nalgene bottles, like the indestructible Nalgene bottle. And nowadays Nalgene bottles have gone out of vogue, and you have your Hydro Flask aluminum bottles instead. And one of the reasons why is because if you made a bottle completely out of polyethylene terephthalate, it would be hard to process. You wouldn't be able to make the bottle. And so they add a little bit of what's called a plasticizer, something that gives it a little bit of plasticity, makes it easier to process, gives it some flexibility when you use it so it doesn't break quite as easy. And there are some concerns with polyethylene terephthalate that the plasticizer is coming out and leaking into your whatever you're putting in your bottle, right? So that's a problem. That said, polyethylene terephthalate is still a very important polymer. It's still used for tons of stuff. It's rigid, it's strong, makes great fibers. It's a decent glass substitute. Polycarbonate we already talked about. Okay, those are the polymers that I think you should be aware of. There are literally tens of thousands of other ones out there. There are so many polymers because there's just so many ways you can put these together, and they all have different properties, which makes it such an interesting and exciting field to work in. Okay, let's talk about molecular weight. You've got these chains, right? No matter what type of polymer you got these chains. You could calculate the weight of that entire chain. Right? That's what molecular weight is getting at. You're calculating the weight of these chains. But the problem is that when you make these things in a batch process, you don't have just one chain length, right? Maybe you wanted to engineer it so they're all exactly, however long, but in reality, they're going to be different chain lengths, right? So instead, what you have is a distribution. So here, you're going to plot the amount of polymer as a function of your molecular weight. Now, if you took the number average, then you have your highest or your average value based off of just the number that had that chain length. And then if you have your weight average, it's going to be shifted to the right, because why? Well, because these ones that are really, really long chains, they're going to weigh a ton. Even though there's only a few of them, they're going to weigh a lot because they're really long chains. These ones are not going to weigh very much because they're really, really short. So this always shifts your weight average molecular weight to the right of your number average molecular weight. Okay, so how would you go about calculating this? You would need an instrument, a tool of some sort, that can basically measure the amount, be it weight fraction or number fraction, that correspond to different molecular weights. So normally what you'll see in a question like that is you'll see a table that says, okay, you have 10 weight% of your polymer is between this chain length and this chain length. You've got 10 weight that's between this and that. So it'll be broken up into a histogram. So you can calculate your molecular weight by considering each section of that. So you're going to take the sum, you're going to do a summation of each section, how much the weight fraction is, or the number fraction, multiplied by the molecular weight of that section. So you'll see some examples of that on the next homework, which will not be due until, I don't know, after fall break, probably the Wednesday after fall break or something. We already talked about degree of polymerization. Again, if you wanted to calculate the degree of polymerization and you knew what the molecular weight of your polymer was, you know that it's like 1,000,000 grams per mole, and you know that each individual mer unit is 100, you would just take 1,000,000 and divide it by 100, and you'd know that the degree of polymerization is 10,000, right? So it's just simply dividing your molecular weight by your mer weight. And because there's two ways to define molecular weight, number average or weight average, then there's two different degrees of polymerization. Okay? Let's keep going. Okay, how about this? Which of the following, this is our next clicker question, which of the following has the highest average degree of polymerization if the number average molecular weight is about 250,000? So that's just A, B, C, and D. Okay, the equation, I'll write it right below here real quick. That's not helpful. We live in 2017. It's amazing. Where M with a small m with a hat, that's your mer molecular weight. That's how much each mer or repeat unit weighs. Big M with the bar on it, that's your total molecular weight, which is the 250,000, right? So the whole thing weighs 250,000 grams per mole. So you're going to divide these things by their mer weight, or rather, just by looking at it, you can do a quick estimation of which one is the highest or lowest and use that to answer the question. Today? No. That's what's dissolving. Exactly. And the nylon's not dangerous. And again, I apologize, we didn't get the spicy Cheetos. Mistakes were made. Okay. Maybe get your answers in the next minute. Phone a friend if you need to. Which of these has the highest average degree of polymerization? Okay, let's work through this one together. Okay, on that first molecule, you could just count it up. You could say carbons. Go back to drawing. Carbons, you've got 2 carbons. Sorry, 5 carbons plus 1. So you got 6 carbons there. And those are each times 12, roughly. You've got 1 nitrogen, and that's times 14. You've got 11 hydrogens. 11 hydrogens. Those are just 1 each. And then you've got an oxygen, right? So you could do the math and figure out what that one is. We could do the same thing on this one. You've got 1, 2, 3, 4 carbons plus 6 in the chain. So you've got 10 carbons there, plus 3 oxygens. This one you've got 2 carbons plus 2 chlorines. Sorry, what's that? Oh, I'm not writing. I'm just going to add this up. I think I'll make any answer here worth credit. Chlorine weighs, I think, 35 grams per mole, so it's pretty heavy. And then on this one, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons. So I'm going to make any answer you gave here worth credit, but it would be not the worst thing ever to actually add these up. It would just take time. Something like that I probably wouldn't put on a test because it would just chew up a lot of time. Fine on a homework, not on a great test. So answer something. I'll make sure that any of these are worth credit. I'll work out the answer after class. I don't remember offhand, and I'll have it posted though. When I do the notes with the scribbles, you'll see the right answer there. I don't know if it is the third one or not. We'll find out. Okay, we've got 5 minutes left. We've already talked about the fact that we can control processing parameters like temperature or the amount of our catalyst that starts this chain reaction. So there are things you can do to change the length of these polymers. I'll just leave it at that. And then I'll say that the melting or the softening temperature is going to be proportional to the molecular weight, right? And that proportionality goes up to about 10 to the 5th grams per mole. So up to around 100,000 grams per mole, increasing it will change your mechanical properties. And after that, it doesn't really change anymore, right? So I think somebody last class asked about how do you go from like a wax to like a solid. Maybe that came up. Well, a lot of it is just based off of chain length, right? So if your molecular weight of your chain is less than 100, you're probably going to be a liquid. This is things like octane, hexane. Those are just carbon chains, but they're not that long, and so they are liquids. If you go between, up to say 1,000, you're probably going to have a waxy solid. So this will be like your, beeswax and stuff. And if you're between 10,000 and a million, it's going to be they're sometimes called these high polymers. It'll be a solid though, right? So it's going to be it's going to be a polymer that's like your calculator case that you can really tap on. It's not going to scratch as easily. It's definitely not going to heat up and melt as easily. It's going to be more rigid and higher melting point. Okay, let's talk about molecular shape. We've been up till now considering these things being long chains. But that doesn't have to be the case. In fact, they can be all sorts of things, right? So you can have your chain, which is long and linear like that, or you can have your chain doing all sorts of random things, right? Because every one of these joints where there's a carbon, it's a single bond, and single bonds, we know that they can rotate, right? So there's sort of this sphere that this thing could have been. Like, it chose to be right there, but it could have been anywhere along that cone, whereas along that cone it's 109.5 degrees, right? This thing could have been the same thing. It's got a cone where it could have existed, but it happened to be that one. So it doesn't have to be that it lines up in a perfect line. It can be a jumble of spaghetti. And more often not, that's the better way to think of polymers, is like a bowl of spaghetti, right? Where the noodles are wrapped all around each other. You can't pull one out because it's going to tangle and grab its neighbors. That's why polymers oftentimes have their elastic properties they have, because if you pull on it and you're pulling on some of those, they're dragging neighbors with them, and as soon as you take that load away, they want to go back to where they were because you were stretching neighbors and stretching bonds. So this is why polymers oftentimes have the plastic or elastic nature that you observe. We could calculate the length of these bonds, right? All you need to know is our formula right here. The length of this chain, if you were to stretch it out, length is equal to n times d. N is the number of molecular bonds along that chain. D is the length of an individual bond, and if you're talking about carbon, that carbon-carbon bond is 0.154 nanometers. That's just about the average bond length of carbon. If we drew the potential well and looked at the bottom of the well, that would correspond to about that distance for carbon-carbon. And then you have to multiply it by this geometric factor that takes into account that, okay, this chain would be longer, but it has these kinks in it, and so we have to reduce it by taking into account that this angle right there is 109 degrees, and it's gone. So that last bit's not there, but that is 109 degrees, right? So you have that term, the sine of theta over 2, that reduces from that. There's some simple geometry there. I think we're going to skip it for the sake of time. And So next time we will talk about a little bit of crystallinity and a little bit more about these structures, and then we'll be done. Are there other questions before the exam on Friday? Any last burning question? Yeah, Arthur? Yeah, good question. There's 3 questions on the exam. One is from last test, and it's on free energy if you saw the study guide. And then you got 1 question on fracture mechanics and 1 on crystal structures. Nothing on polymers for this test.